Today's lesson is on weighted graphs. The lesson objective: I can use graphs and the definitions of circuits and paths to determine the best solution to certain situations. I can use assigned values or weights on edges to determine the most efficient path. Let's review quickly. An Euler circuit is a graph where it is possible to start on a node, travel every edge exactly once, and return to the original node. An Euler path is a graph where it is possible to start at a node, travel every edge exactly once, but end on a different node. The degree of a node, the number of edges that enter that node, including edges that enter both starting and ending on the same node, which means that they would have extra 2 degrees for that. Anyway, I misspelled the word enter there. I will have to fix that for the future. For the review, an Euler circuit and path can be determined by the degrees of the graph. The degrees of the nodes, actually. An Euler circuit has only even number degrees for every node of the graph. And an Euler path has 2 odd number degrees, and the rest are even number degrees. And a graph that has 3 or more odd number degree nodes can neither be an Euler circuit nor an Euler path. That's not review. That is not defined here, but I needed it to be said so that you can be reminded of it. All right, so weighing a graph. The weight on a graph is a number of value that is associated with an edge on the graph. So if we look here, this edge between A and B has a value of 1. This edge between B and D has a value of 3. And this edge between A and D has a value of 4. So in a real life scenario, let's think of it this way. Let's say this is city A, this is city B, this is city C, this is city D, and this is city E. And these are all toll roads between all the cities. So city A and B only have a toll of 1 to get between them. But city A and D have a toll of 4. So a weighted graph is a graph which all edges have assigned values to them, and that's what this is. So if we wanted to determine the least expensive route between A and E, we look at all pathways between A and E and see which one was the least. A, D, E is 5, 4, and 1. A, C, D, E is 3, 1, 1, or 5 also. A, B, D, E is 3, 4, 5. That's also 5. So how about A, B, E? It's 1 and 2. That's only 3. So there are lots of other pathways, but you can easily determine the most efficient, or the least expensive in this case, valued route. All right, so let's talk about the snowplow problem. I've been teaching this course for a couple years, and I realize that down in Texas we don't get a lot of snow. So if you have a problem thinking about how a snowplow operator must work and be efficient, plowing snow off the road because it doesn't apply to Texas, think of this as a street sweeper problem. And we have lots of street sweepers down here in Texas. So let's say a street sweeper must decide the best route through the cities he works. In each of the cities he works, he has to sweep all the roads and return to his starting place. We also must keep from backtracking as much as possible. So let's look at this. The best way through a city is to know whether an Euler circuit or an Euler path exists, because all edges have to be touched exactly once. So in this case, let's think of it. Is there a pathway where the street sweeper can go through the city at all intersections and touch every street just once? And the best way to know that is check for an Euler path and an Euler circuit. Most optimal in this situation would be an Euler circuit where we start and end at the same vertex or node. And in this case, let's look at the degree of each vertex. How many edges are entering A? Let's see. BA, that's 1. CA, that's 2. And EA, that's 3 edges entering node A. So that is a degree 3, or an odd degree vertex. How about vertex B? AB and CB are the only edges going into B, so that is an even degree of a degree 2. How about C? There's BC, AC, EC, and DC. All of those edges, there are 4 of them. So that means C is also even. It is a degree 4. D has CD and ED going into it, so it's also even, only has degree 2. And then finally E, the last one we looked at, it has AE, CE, and DE, meaning it is an odd degree vertex. So let's go back to the definitions and find out which one it is so we can look at it and review. An Euler's circuit has only even degrees. Well, we know we have some odd degrees, but an Euler path has 2 odd degrees and the rest are even. Well, if we look at that, we said A and E were odd degreed and the rest, B, C, and D, were even. So we know that an Euler path exists. So the way we're going to do that, and we'll go on to the next one so we can look at it, and it's still there. Vertex A and E, both degree 3, which is odd. B and D are both degree 2 even, and vertex C is degree 4, just like I discussed. 2 odd degree vertices and the remaining vertices even falls in the definition of an Euler path. So, in order to find the path, we are going to start at either odd degree vertex. It doesn't matter which, but either one, A or E, okay? So, we're going to find the path that is going to cover every edge exactly once. So, I've got a pathway here that covers it. There's more than one path. So, AB, BC, CA, AE, EC, CD, DE. Now, the problem with this snowplow or street sweeper problem is we got to put that street sweeper back on the trailer and we left it at A. So we got to go back to A. Now, we have always learned in mathematics that the shortest distance between 2 points is a straight line. That would be EA. But in this case, we're talking about a model, not the exact situation. So as you can see, EA has a value of 7 assigned to it. But there is another pathway from EC and then CA that has a sum of values of 3 plus 3, or 6, which is less than 7. Now, despite what this model looks like, that pathway is more efficient, and that would be the pathway we would take. So, let me launch you with this. When you decide to go to the RenFest, now you can use what you just learned to find the most efficient path to all the cheap booths you wish to visit, saving you money, time, and worn-out legs. Okay, so have a great day, folks.